Hello. Hi, everybody. I hope everybody can hear me.
All right, so we have Alex here, CEO and co-founder of Matter Labs. He'll be doing a talk on zkSync, scalability for turbulent times. Can you guys just confirm in the chat that you can hear us, and he will be able to start presenting?
So can everybody hear us? I think we have some echo problem. Is it on my side?
It's on your side. So you probably have another extra window open.
Oh, right. So let's try this. Is it better now?
Perfect.
Okay, great. Sorry, guys. So yeah, hi everybody. I'm Alex. I'm gonna talk about rollups. Just as a previous speaker, unfortunately, I couldn't participate because I was in my green room. But I maybe will take a different angle at this problem and try to look from more from the perspective of zkRollup. So let me share my slides. Okay. So I hope you can see it all. I'm going to start with what's is going to be in this talk. So we'll talk about the scaling problem in general and why it's important. I will give an alternative explanation of what rollup is, compare optimistic and zkRollup. I will show you the latest status of zkSync and also show what you can do with smart contracts on the zkRollup. And the audience for this talk is mostly technical, but I'm going to give a non-technical explanation as far as possible. So I'll try to make it balanced. And let's start. So it's not really possible to scale applications right now on Ethereum simply because Ethereum doesn't support massive scaling is just out of question. It's been a problem since CryptoKitties. For a couple of years, we see only linear growth of Ethereum users, or even Ethereum unique addresses, which is even less than users. But the demand is there. Demand is enormous, and we can see it with all the soaring DeFi applications. But this is just a part of the problem, because in times like Black Thursday, when the lot massively peaks, we see that there are a lot of issues emerging from the lack of peak capacity. So if you're familiar, if you follow the news on the Black Thursday, the transactions between exchanges were limited in volume. It created a lack of liquidity. It caused a lot of it caused some cascades of liquidations on decentralized platforms which couldn't keep up with the load, and it created some really bad outcomes. So it almost killed MakerDAO, for example. And although you could have increased transaction prices accordingly if the software was working correctly, it would still cause a lot of disruption for protocols which rely on smaller transactions, like 50 cents, $1 transactions, to be able to come through in these peak times. So imagine your application, it just goes down for 2 hours, 1 day, and you cannot do anything. So it would be a catastrophic event. So you want to plan for this. You want to have a solution which will allow you to grow organically, grow exponentially, hopefully with a viral load of your application, and then also be able to respond to these highly intense moments. So we have multiple solutions for scaling right now. I think Rollup is most interesting from all perspectives, and I'm going to give a new definition of Rollup, a non-technical one. I would argue that Rollup is anything which is generic layer 2 with permissionless recovery on layer 1. So what it means, generic is you can essentially do anything you can do on layer 1. So like whatever use case is programmable on layer 1 should be also programmable in Rollup. Under this definition, payment channels, for example, do not fall because payment channels are only bidirectional transfers. So you cannot build smart contracts, for example, and you cannot build some more complex scenarios. You have other solutions which are generic, like side chains, but they're not permissionlessly recoverable. So you cannot have a guarantee that the money which you put in such a system will be retrievable on layer 1 without some severe trust assumptions. So with the sidechain, for example, you would have to rely on the majority of the operators to be honest. So with Rollup, we will see that different rollups have different properties in this regard, but generally, it should be possible for end users to get their money back no matter what the operators do, like without reliance on the operators. So if these two properties are fulfilled, then we have a rollup. So there are multiple flavors of rollups. I'm going to focus on two, but I'm just going to explain technically first how a rollup works in general. So the idea is that you have a smart contract on Ethereum on some layer 1, which holds the root state of the state root, so the root hash of the state, which is maintained somewhere off chain in some databases run by operators, maybe partly also by end users. You have accounts as leaves of this state, and then you have a root hash which represents a cryptographic fingerprint of the entire state at any given moment of time. And this contract also holds all the funds for the rollup in one single pot. So you have just one Ethereum balance which has all ETH, you have one DAI balance which holds all DAI, and so on. And who owns what in a rollup is then figured out by the state. Now, how the transactions work is user creates a transaction, signs it, and submits it off-chain to the aggregator or to the operator of the rollup or to one of the operators. It's just being sent on not through Ethereum, but through some either to the server or through some peer-to-peer network, no matter how. The aggregator then packs many transactions in a single block. And the block consists of some very specific information. So first of all, it contains the new state root hash after all the transactions have been applied, which is computed by the aggregator. Then it contains the state delta, which is all the information which users need to process on Ethereum from the logs or from transaction history to be able to reconstruct the state tree at any point of time. And then it contains some proof data, which will allow us to make sure that the state transition is correct. So it's different from different flavors of rollup. I will talk about this later. But for now, we just have these three components. Okay. So this block is submitted to the mainnet, to layer 1. And what happens is the processing of this block by layer 1 is much cheaper than the processing of each individual transaction would have been if we submitted them directly to Ethereum. So in terms of storage, all the smart contracts on Ethereum needs to do is to update the root hash. It's of one operation. It's just one operation, no matter how many transactions we pack there, maybe thousands. On the computation side, for optimistic rollup, we do nothing. For zkRollup, we verify the SNARK proof, but it's always a constant amount of work. So computation also scales exponentially. No matter how many transactions, we do all the same piece of computation for every block. The only thing which grows linearly is call data, because we need to publish the state delta, and state delta grows together with the number of transactions. So it's linear. And this is the cost for having the data ownership. So the big leap of Rollup comparing to Plasma was that the data is owned by users. And we used Ethereum or layer 1 to broadcast this data to make it available to everybody and solve data availability problem this way. And this is what enables you to completely not rely on operators. Because if you rely on them, they will have the right to censor your transactions. Like if you don't own the data, and if you don't have a means to let it available to other users,
Hey, Alex, it seems your screen may have frozen. Do you mind refreshing your browser? I can see your screen, but they're saying there's no audio from you. Yeah, he can see your screen now. Can you hear him? No audio, 50% there. No sound. All right. Yes. Sorry, guys.
Can you hear me now?
Yes.
All right. Sharing my screen.
Yes, you're here. Can you guys hear him?
Now I can switch off the video.
Perfect.
And turn on the screen. And go to Keynote. So can you see it now?
Yes, and they said the last statement they heard was data is owned by users and broadcasted on ETH network does not rely on operators to own because they can censor, modify.
Okay, so
and that's
this
when they
is
lost
the screen which we probably, this
Yes.
was the last screen. Okay, so I will quickly recap from here. I'm sorry guys for this. It's 8 o'clock in the morning for me from Europe. Maybe I was not in best state. So you pay the price of data ownership by submitting linear amount of transactions on Ethereum in terms of call data. But call data is cheap. It's much, much cheaper than storage. It's a lot cheaper than computation. It's just essentially a couple of bytes per transaction. It's different between the different versions of Rollup. So for optimistic Rollup, it's significantly more because you have to submit the signatures. For zkRollup, it's less because you only need to submit the delta. But in both cases, it's much cheaper than the full computation. So okay, I'm going to talk about two flavors: optimistic and zkRollup. With optimistic Rollup, anybody can call the police and say the transaction was fraudulent, but operators can essentially make state transitions whatever way they want. With zkRollup, users authorize every transactions before they happen on Ethereum. And the way it works is for optimistic Rollup, you submit the state delta plus the proof data for every transaction, like a signature, which can be then used by the smart contract on the mainnet when a fraud proof arrives to verify that the block executes exactly right. So like every transaction is going to be checked during the fraud proof check for the correctness of every signature. And this is why it costs significantly more to operate optimistic Rollup because you have to submit signatures, which they are big. They are like 64 bytes of data for every signature. With zkRollup, we submit one single SNARK, no matter how many transactions. And this SNARK already verifies all signatures for all transactions and all other things. Like it verifies that the balances were correct, that the accounts were updated correctly, and so on. And this proof is checked before the state transition happens on Ethereum, whereas the fraud proof happens after an incorrect state transition happened and was indicated by someone. And this is the difference. So in an optimistic Rollup, somebody has to monitor it. If users have to monitor it, you would have higher security. But if every user monitored every transaction, you would essentially have plasma. It would not scale. Like it defeats the purpose of any scaling solution because then everybody has to do the same amount of work. So the idea which can work is that you have a lot of operators with a stake, and they all have to monitor each other. And if at least one of them is honest, then you can expect that they will spot the invalid transaction and create fraud proofs. So for this to happen, you really need to have a lot of them. You cannot rely on just 10 or like one operator. And it gives some advantages, this approach. So it's easier to implement EVM-compatible state transitions. So it's feasible to take existing EVM code and port it on the optimistic Rollup with minimum modifications. So this is one big upside. But you have a couple of downsides besides this basic security risk. So number one downside is that your exits will always be locked out for at least a week. So I personally consider a secure lockout period 2 weeks. I heard a lot of optimistic rollup implementers talking about 1 week. They plan 1 week, but at least 1 week is the time which you will have to wait before you can withdraw the funds from the rollup, because you need to give opportunity to other users to spot a fraudulent transaction and submit fraud proof. If the time was shorter, it would be trivial to run a denial of service attack on the rollup, execute a fraudulent transaction, withdraw all the funds, and not let anybody submit the proofs. So this is a big inconvenience. But then you'll also have various attack vectors on this rollup. So first of all, it can be honeypot for hackers. If you have a lot of funds in the rollup, they can try to break the operator's servers and shut down the monitoring tools, which might be hard because you don't know where they are located. So like the operators can run some hidden server somewhere in internet, but it's still possible if you have a few operators, not a lot of them. So you might try to infiltrate them with some agents or some spy stories. So this is one risk. Another risk is that it's possible to run a coordinated bribing mechanism for miners and incentivize miners not to include the fraud proofs for this 1 week lockout period. So this is hard because it's essentially equivalent to a 51% attack on the mainnet, except that the cost for miners is essentially negligible. So the only risk the miners are taking is some risk of social persecution. If this becomes apparent to the community, there might be some outrage in the community, but the benefits might outweigh the risks. So it might still be a problem. And miners are not your friends. We know a lot of things about miners, like how front running is happening. These things. It's a big risk. And finally, you never see the security mechanisms in action in the optimistic case. So if everything is good, the system is running, you never see how fraud proofs execute because there are no fraud. There is no fraud happening. So you can actually never be 100% sure that they will work as intended. So you might want to inject random fraudulent transactions and see whether they are going to be spotted, but this will disrupt the operation of the service. So it's just something you have to be aware of and pay attention to. Now with zkRollup, it works differently because you have proofs of validity rather than fraud proofs. They have to be submitted before the transaction is executed before the rollup block is accepted by the Ethereum mainnet. So the operator can never do anything wrong. They can't be evil. It's not about don't be evil, it's about can't be evil. So the upside for this is we have a very fast finality because the blocks are executed as soon as we have a zero-knowledge proof, and on average takes for now about 10 minutes. A single operator can be secure, so you can bootstrap a system with just one operator, and there are no attack vectors other than just trying to break the cryptography. But we use very well-known cryptography, so it's more a mathematical problem rather than game theoretical or hacking problem. The downside is that we cannot easily port EVM, so you cannot take your Solidity wiper code and build contracts on it. But I'm actually not sure that this is a big downside because there are just better languages than Solidity. So we'll talk about this a bit later. But zkRollup also has unique properties which can only be implemented with zkRollup. That is privacy, for one. So you can have confidential and completely private transactions, which would be at least 1,000 times more expensive on an optimistic rollup. And we can also reach real-world capacity of tens of thousands of TPS. And there isn't, without losing any properties of the rollup. So it's not a trick, it's not just some hype. It both works due to recursive verification of SNARK proofs. So we can create a SNARK proof which verifies a couple of other SNARK proofs, and they can verify other proofs in turn. So we can build this nice Merkle tree of SNARK proofs. And the way it would work is, instead of submitting the state delta for every transaction, we can submit a state delta per account. So we can tag as many transactions as we want, which are coming from one account, and we just submit one hash per account. So this way we can submit maybe, let's say, data for 1,000 accounts on Ethereum and execute 1 million transactions underneath, because each account will contain 1,000 transactions by this account. And the proof is still going to be singular SNARK. Okay, so about cryptography, we don't have much time, but we have two candidates which can be used. So we probably will launch zkSync right now with Plonk, which uses a universal trusted setup. And there's been a ceremony run by Adstack protocol last fall, where Ethereum Foundation participated, Consensus, Matter Labs, a bunch of other prominent organizations. And the upside is you can always add contribution on top. So if you're not sure that this trusted setup was correct, you can always just add your, you can participate yourself and be 100% sure. Alternative solution is a Redshift protocol, which was developed by Matter Labs, which is completely transparent, but it has a trade-off of bigger proof sizes, which still verifies relatively fast on Ethereum, but we still have to run evaluations and see what's going to work better. Okay, so zkSync. zkSync is our implementation of zkRollup protocol. It's in the final stages of the security audit, and we're going to launch it very, very soon on the mainnet. For now, it supports ERC20 and Ethereum transfers, just token transfers. It has a very simple UI. It has simple SDK. It supports Matter transactions, so users don't need to own gas or pay for gas. They can just create an account without any interaction with the mainnet, receive money, withdraw to the mainnet, all like in matter of seconds. And then after 10 minutes, transactions are final there. And it also have an N-of-N multisig support, because we use a MuSig scheme, which is a convenient way to aggregate signatures on chain. So I wanted to show you a quick demo, but we are really running out of time. So let me just check quickly. Okay, I'm just gonna try real fast. So it works with MetaMask. I'm not going to make a deposit because it will take too long. We'll show you how transfers work. So you could just make a deposit from the mainnet. The funds will appear in the rollup. Then you can go to a different browser. Let's go here. I can log in with so I have an existing account. I can try to create a new account so that you can see how it works with a fresh one. So I have a completely fresh account. 1 second. Okay, it's a demo time button. Yeah, so I have a completely fresh Ethereum account, which has no Ethereum transaction history whatsoever. I can copy its address, go here, and make a transfer of some tokens or Ether. I will confirm in MetaMask. Okay. I will use an older client because the client is it's a new one and it's still in debugging actually. Yeah. Send a different account, different amount. Then we go back here and you can see that we got some money already here and it's very fine. And after 10 minutes, when the proof is generated, you will be able to immediately withdraw this from the mainnet. So you're welcome to try the older version of the client, which is not as beautiful, but it's working completely stable under the link which I submitted in the chat in the beginning. It's zkSync.io, and for now we support only token transfers. In the near future, we're going to add smart contracts. Later, privacy will come into play, and eventually we want to completely decentralize the protocol. So for now, we are operating zkSync as a centralized operator. It poses no threat to the security of protocol, which I explained before, but it's not nice from the decentralization standpoint because we can still, users will have to rely on us for the smooth operation of the service. They don't rely on us for security. They can always withdraw without our cooperation, but we want it eventually to work also without reliance on any single party for the normal operation. But it's a future. For now, non-custodialness is the key, and it will be possible to support smart contracts with Zinc, which is a Rust-like language inspired by Libra Smooth. Zinc is completely functional. You can try it out. I also posted a link in the chat. It was designed with Rust philosophy in mind, so the safety is first. There are no operations which are unsafe in like arithmetics or in like all the constructs are built in such a way that safety is assumed. So you cannot make an overflow. You don't have to think about any details of zero-knowledge proofs which are running under the hood. Sync will take care of it for you. It's also designed to be simple, much simpler than Rust. So it's easy for users of Solidity and JavaScript and whatnot to come over to Sync and start building. Yet it's pretty expressive. So it has a lot more expressiveness than other zero-knowledge proof languages and even Solidity. So we support structs and tuples and immutability and all the nice features of Rust, which makes Rust lovable by developers who love Rust. And if you hate Rust, don't worry, we removed all the elements which you normally hate there. So smart contracts are yet in alpha, so we're just experimenting with them. I can show you a code of a clone of Uniswap written in Zinc. So it's completely functional. It compiles. It's not functional yet. We cannot just run it on chain. There's a lot of things which need to be implemented in order to actually run the smart contracts on zkSync. But it already compiles, and you can see things which, like elements of the language, which will be supported. So for you, just to have a mental model, the programming model of Zinc for smart contracts will follow the exact same conventions which are used to in Ethereum. So you just define the contract, you define some state variables. They might be complex, so you can use, you can redefine types for convenience and for type safety. So it's 100% strictly type safe. You define public methods, you define some private methods, and then you just work normally as though you just, the way you would write a normal smart contract in Solidity. No special knowledge, no special handling is necessary or will be necessary there. All right. So I think we're almost done, and it's time for questions now. Coming back. So which ERC20 tokens will be supported? We will support the bunch of most popular ones from other protocols. And for now, we have a white list of tokens, but you can just talk to us and we'll add your token. Eventually, it will be permissionless. Anybody will be able to add any token without asking us. But for now, you just have to ask us because we want to launch the system initially gradually so that we don't run into some unexpected problems with some fraudulent tokens and so on. 10 minutes finality. Well, it's what do you compare it to, right? So in optimistic rollup, the finality is 1 week. In zkRollup, it's 10 minutes, but you will have a confirmation before. So you will essentially have an instant confirmation of your transactions. We will give you a promise that the transaction is going to be included in the next block, and then we will do our best to include it. If like 10 minutes is the time which takes the proof to be generated, and once it's there, your transaction is 100% secure, backed by Ethereum. So it will have the same finality properties as Ethereum. Before that, we would theoretically have the chance to revert it, but we will also introduce in near time instant confirmations with a security bond, which will provide economic finalities much faster. So it's essentially instantly. Okay. Could you say a little bit more about the data availability problem? So data availability is what stopped Plasma from being implemented. So imagine, let's go back to, so yeah, last question, Zinc is released. The link to Zinc is, all right. I'm gonna post a link here.
Hey, Alex, we can let you do one more question if you have any that you want to answer.
Yeah, I just submitted a link to Zinc. Data availability, I'm going to answer this one, and then we're done. So you have some state, right? The state is represented by a number of accounts with some data, accounts and balances. And then you construct a Merkle root of the state with a Merkle root hash representing the state. So if you change anything in the underlying state, the path from the leaf which changed to the root hash will change. And if users don't have all the individual leaves in this tree, they will never be able to reconstruct the root. So if something changes and somebody, the one who made the change did not inform you about the change they are making, you will not be able to prove that you have your account in a specific state included in this root hash. You will just see a new root hash. You might have a zero-knowledge proof that this root hash is correct, so you may be sure that your account is in there, but you just cannot prove it to anybody else. And this is the data availability problem. And this is why Plasma failed, because it's hard. Like there is no way to convince somebody that I informed you about some data and you didn't get it. So if you like, you cannot come to somebody and say, Alex did not give me the data, because I can always come and say, well, I gave him the data. He just pretends he didn't receive it. So the only way we can make it solve this dilemma is by broadcasting the data on some channel which we know is publicly available. And such a channel is Ethereum call data. So once it's on call data, anybody who runs full Ethereum node can go through transaction history, pick this transaction, check the call data, and then grab all the updates from there, reapply them, reconstruct the root hash, and or like reconstruct the state. From this state, that you can reconstruct the proof for your account in this state, and this way you can retrieve your data. So I hope it was a good explanation. Otherwise, I just will refer to, just Google data availability and Plasma, and you will get the answer.
Awesome. Thanks so much, Alex, and apologies for the technical issues. We're
My
going
apologies.
to, no worries. All right, so we're going to transition to the next talk now.
Yeah, thank you very much.